Good afternoon and welcome to the CLEAR webinar series. This is Dave Dixon, Extension Educator here at CLEAR. We are happy to bring you today's presentation, More Than Just a Picture, the Basics of Remotely Sensed Imagery, with our very own James Hurd and Dan Civco. Thanks for joining us today. This is the fifth presentation in the 2015 CLEAR series. You can see all of those titles there that are kind of shadowed out. Our past webinars that we've already held, and those are all recorded and posted on our website, which you can get to at clear.uconn.edu. And you see there today's remotely sensed imagery webinar. And then we have a slew of webinars coming up this fall as well that will be starting around mid-September, and we'll be announcing those probably in the next week or so. And so that's it for opening statements, and now I'm going to turn it over to James and Dan to take us into today's presentation.
Thank you, Dave. Good afternoon and welcome to our webinar on More Than Just a Picture, the Basics of Remotely Sensed Imagery. I am James Hurd and I'm here with Dr. Daniel Civco. We are both from the Department of Natural Resources and the Environment at the University of Connecticut. I want to acknowledge that this webinar is sponsored by Connecticut View and CLEAR, the Center for Land Use Education and Research. Connecticut View is one of about 51 state views who are part of the America View Consortium. America View is a nationwide program funded through the USGS with a primary purpose of promoting and educating the public about the use of remote sensing technology. Connecticut View received initial funding this past year, so we are just in the beginning phases of development, so stay tuned as we continue to develop our programs. You are all probably familiar with CLEAR, but just in case you are not, CLEAR was started in 2002 with the mission to provide information and assistance to land use decision makers and other audiences in support of better land use decisions, healthier natural resources, and more resilient communities. CLEAR is comprised of various departments and programs within the University of Connecticut. To start, I came across this quote attributed to Socrates, the classic Greek philosopher who died in 399 BC. He states that man must rise above the earth to the top of the atmosphere and beyond, for only thus will he fully understand the world in which he lives. I thought it profound that a mind from so long ago would recognize the value of viewing the earth from above, that it would allow us to better understand the world in which we live. Remote sensing is the tool that allows us to do just that, view the earth from above so we can more fully understand the world in which we live. The value of remote sensing is that it provides us with a synoptic view of the world, including spatial relationships between features and temporal changes and trends that allow us to monitor and analyze natural and human-induced phenomena, such as deforestation and forest fragmentation, as shown in these two images of Rondônia, Brazil. A dam was constructed on the Imagery River in 1984, shown in the left, leading to upstream flooding of the forest and subsequent clearing and development of the surrounding area, as shown in the 2011 image on the right. Urban expansion, as in this example of Manila, the capital of the Philippines. These images from 1989 on the left and 2012 on the right show the expansion of the built-up area, shown in the purplish colors. The impacts of growing population create serious infrastructure and environmental problems because of the dense development. The Pasig River, which cuts through the urban area, is one of the most polluted rivers in the world. The impact of forest fires such as these in Alaska. The image on the left shows the scar left by the Dry Creek fire that burned over 48,000 acres during the summer of 2012. The image on the right shows the nearby Stewart Creek 2 fire that started June 19, 2013 and burned over 85,000 acres. Impacts of natural hazards. These images are from Tuscaloosa, Alabama, and show the impact of an EF5 tornado that hit the area on April 27, 2011. The tornado path can be clearly seen in the 2011 image on the right. Coastline impacts, as shown with the growth of a delta where the Atchafalaya River flows into the Gulf of Mexico. The delta was formed by deposition of sediment following the construction of a canal through Wax Lake in 1941. Since Hurricane Katrina in 2005, it has also served as a model for delta regrowth in the Mississippi River Delta region for restoring wildlife habitat and protection against storm surge. Estimating water quality, such as in this example from coastal Vietnam, where chlorophyll A concentrations are monitored over the span of a year. Chlorophyll A concentrations are a sign of eutrophication, which results in decreased water quality. The reds and yellows show dates of increased chlorophyll A concentrations. We can use remote sensing for cropland assessment. Not only can remote sensing be used to identify crop types, it can be used to examine the stress level of the vegetation so corrective actions can be taken. In this example, the red areas are areas of stressed vegetation. Those are just a few of many uses for remote sensing. In order to effectively use remote sensing, however, it is important to understand the technology and what the images are showing us. So the primary goal of this webinar is to provide you with a general understanding of the remote sensing process and data so you are better equipped to identify potential uses of remotely sensed imagery and understand their benefits and limitations. Here's the basic outline for today's webinar. Our plan is to discuss what is remote sensing. We'll look at the basic process, describe the 4 resolutions of digital remote sensing imagery, identify some typical remote sensing sensors and their images, identify sources of remote sensing imagery specific to Connecticut, and touch on some processing that can be performed on these images. So, what is remote sensing? As Dr. Civco defines it, remote sensing is the art and science involving the detection, identification, classification, delineation, and analysis of Earth's surface features and phenomena using imagery acquired from terrestrial, aircraft, and satellite platforms equipped with photographic and non-photographic sensors using visual and computer-assisted interpretation techniques. But really, it is just the process of gathering information from a distance, whether that be through the use of your unaided eye looking across the landscape, or through the use of some sensor aboard a platform in the sky or in space that is collecting energy to form an image of the Earth's surface. In addition, I would be remiss if I did not mention the growing popularity of the unmanned aerial vehicle, which is allowing users the ability to quickly and cost-effectively collect aerial images of targets of interest. Remote sensing is part of the geospatial technologies, or geomatics, which includes geographic information systems, which most of you are familiar. It is geospatial because data have a geographic or locational component associated with it. This is typically provided in the form of coordinates, but can also include addresses, a city, or zip code. A location on one geospatial data layer will be the same location on other geospatial data layers, which will allow us to analyze spatial information and answer questions such as, what is at a specific location? How much of that is there in this area? And what has changed from this date to that date? With remotely sensed imagery, we typically deal with coordinates. The image will represent a portion of the Earth's surface based on its coordinates, and from the imagery we can identify what is at a specific location. Typically, remotely sensed imagery is a layer within a GIS, or data products derived from remotely sensed imagery are included as data layers in a GIS. To understand remote sensing, you need to understand the basic process, as shown in this graphic. First, a source of electromagnetic energy is needed. Typically, it is the sun that provides the visible, infrared, ultraviolet, thermal energy that we tend to detect in remote sensing. The sun represents a passive source of energy. We can also artificially generate a source of energy that is then detected, such as with radar, LiDAR, microwave, and sonar sensors. We call these active sources. Second, you need a device that collects the electromagnetic energy that is returned from the surface of the Earth. These can be handheld, aircraft-based, or satellite-based devices, and they can collect imagery through film with a camera, such as with traditional aerial photography, or through some form of a sensor with a detector array that converts solar radiance to a digital value for a given pixel unit, producing a digital image. We will be focusing on digital sensors in today's webinar. Lastly, the big unknown is what is happening to the electromagnetic energy coming from the energy source to when it is collected by the sensor. That ultimately determines the makeup and the quality of the resulting image. Well, it is not completely unknown because we do know that about half of the incoming energy is reflected by or absorbed by the atmosphere due to the water vapor, particulate matter, and gases that are found there. Once the energy initially passes through the atmosphere and reaches the surface of the Earth, it will be transmitted through, reflected and scattered by, or absorbed by various features on the surface. Reflected and emitted energy will again be scattered by the atmosphere before reaching the sensor. It is the distinctive character of electromagnetic radiation reflected or emitted from natural and human-made features that allow us to view and image and identify the various features. In this graph, you can see how different Earth surface features reflect and emit electromagnetic energy. Water has low reflectance in the visible blue portion of the electromagnetic spectrum, with less reflection into the near-infrared. Earth or soil is highly reflective in the visible portion of the electromagnetic spectrum, then becomes less reflective in the near-infrared and middle infrared. Vegetation has some reflectance in the visible part of the spectrum, particularly the green region, but is highly reflective in the near-infrared portion of the spectrum. This is a unique characteristic of vegetation, the high reflectance in the near-infrared. In an image, we can see how the different features appear in the visible and near-infrared portions of the spectrum, as shown in these two images. Further out on the spectrum, you can see how a ground surface emits more energy in the form of heat than water. Looking at the thermal image here, you can see the distinction between water, the dark features, and land, the brighter features. Moving on. Next, I would like to discuss more specifically the characteristics of remotely sensed digital imagery, specifically the 4 resolutions of imagery. It is these resolutions that make images similar or different from one another and determine what might be their capabilities. When we describe remotely sensed imagery, we tend to define the imagery in terms of its 4 resolutions. These include the spatial resolution, the spectral resolution, the temporal resolution, and the radiometric resolution. Spatial resolution refers to the fineness of detail that the imaging sensor is able to detect. That is, what is the smallest object that can be detected? As a digital image, we are describing the size of a pixel or picture element. We often talk about digital images having, for example, 1 meter spatial resolution, meaning that a pixel represents a 1 meter by 1 meter area of the Earth's surface. As remote sensing analysts, we sometimes refer to the spatial resolution of an image in terms of an image having fine or high resolution, with pixel size less than 5 meters, moderate resolution pixel sizes of 10 to 60 meters, and coarse resolution with pixel sizes greater than 100 meters. For a comparison of pixel size, we have drawn boxes to represent pixels of various sizes over a standard American football field. You can see that a larger pixel, such as that from the Landsat multispectral scanner sensor at 79 meter spatial resolution, covers almost the entire football field in 1 pixel. As pixel size gets smaller, multiple pixels will be necessary to cover the entire field. At 60 centimeters, the QuickBird sensor requires thousands of pixels to cover that same area as the multispectral scanner pixel. What becomes important when thinking about pixel size is what are the objects that make up that pixel. An aircraft or satellite-based sensor simultaneously samples multiple spectral wavebands over a large area in a ground-based scene. Each pixel in the resulting image contains a sampled spectral measurement of reflectance, which can be interpreted to identify the materials present in the scene. The 3 graphs to the right illustrate the spectral variation in reflectance for soil, water, and vegetation. A visual representation of the scene at varying wavelengths can be constructed from the spectral information by viewing the different bands of the image. In an image with high spatial resolution of, say, less than a meter, a pixel is typically composed of a single feature such as vegetation, pavement, or water. Yes, there might be some mixing of features at the boundary between 2 feature types, but this generally does not cause any issues when viewing the image, and the edges appear sharp. As the spatial resolution becomes more coarse, that is, the pixel size gets larger, the likelihood of pixels being comprised of multiple land cover features increases. The spectral reflectance values of a particular pixel is comprised of the features making up that pixel. In addition, as pixel spatial resolution becomes larger, we lose the sharpness of the boundary between features. As spatial resolution continues to get larger, pixels are even more likely to be comprised of multiple features, and feature boundaries become non-existent, but spectral data is still informative in these types of images. To look at pixel composition a different way, let's say the red box here represents a 30-meter pixel. It is comprised entirely of water. Here's a spectral curve that represents the reflectance characteristics of that water pixel over the visible and near infrared wavelengths. Here's another 30-meter pixel, this one comprised entirely of vegetation. Here's a vegetation curve. It is vastly different from water, being highly reflective in the near infrared. And here's a third 30-meter pixel example. This time the pixel is comprised of roughly half water and half vegetation. Both the water and the vegetation will comprise the reflectance characteristics of this pixel. The reflectance characteristics of this pixel might look something like this. Imagine what the reflectance curve for this pixel might look like. It is much more complex since it is being influenced by water, vegetation, bright concrete, darker asphalt, and some soil. Plus, if you notice, the building structure is casting a shadow, so that will also influence spectral reflectance characteristics for this particular pixel. Spectral resolution refers to the range of wavelengths to which a sensor is sensitive. As a digital image, we are describing the number of discrete bands and the width of the bands that are available for visualizing and analysis. The sun produces a broad range of electromagnetic radiation. Our eye is designed to see only a small portion of that radiation or energy in the visible part of the spectrum, blue, green, red. As you can see in the graphic, there is much more energy out there that we cannot see with the unaided eye. Sensors are designed to detect energy from these other parts of the spectrum. The spectral resolution of an image describes how many spectral bands are provided in an image and how wide is the collection per band. For example, a panchromatic image has a single band or grayscale that might be collected over the visible wavelengths. Other sensors might collect 3 narrow bands in the blue, green, and red wavelengths, allowing us to view the image in true color. Sensors can also collect data in other wavelengths such as the near-infrared, shortwave infrared, and thermal areas. This graphic helps illustrate the locations of various spectral bands collected by 3 different sensors, MODIS, OLI, and ETM, and the width of the bands within each part of the spectrum. All sensors collect blue, green, and red energy at roughly the same bandwidth as shown on the left. All sensors collect near-infrared energy, but at slightly different band widths. In the shortwave infrared part of the spectrum, there are additional differences in the sensors, with some sensors collecting more bands and other sensors collecting fewer bands at different widths. And lastly, these sensors also collect thermal energy, but again at different band widths. Overall, similar but different in terms of the spectral characteristics of these 3 sensors. With temporal resolution, we are describing the time interval between data acquisitions, or the revisit period. Aircraft-based systems are periodic, being flown when necessary. Satellite systems are more systematic, having revisit periods every few days depending on the capabilities of the satellite and sensor. A Landsat satellite will revisit a location every 16 days. Other satellite sensors can be pointed off nadir to give more frequent coverage of a location. Temporal resolution also refers to the seasonality of an image. Time intervals are important because they allow us to monitor any change in the landscape over time. For example, this area near the mouth of the Connecticut River in Old Lyme, pre-Storm Sandy. And post-Storm Sandy. You can see part of the protective barrier beach has been washed out in the yellow oval. Temporal resolution also refers to the seasonality of an image. In temperate regions, we might talk about leaf-off imagery, late fall or early spring, and leaf-on imagery during the summer growing season. Imagery can look very different during various seasons of the year, such as with these two images from 2008. If you are interested in identifying wetlands, leaf-off imagery would be more suitable since the wetlands won't be masked by vegetation. Agricultural uses would likely want leaf-on during the growing season. Lastly, radiometric resolution refers to the number of brightness levels that can be detected within each spectral band. A full-color 24-bit image can have as many as 16.7 million colors. An 8-bit image can have as many as 256 colors. A 4-bit image has 16 colors, and a 2-bit image will only have 4 colors. When viewing an image at 24-bit or even 8-bit, our eye is not able to discern all the different levels. As an image provides lower radiometric resolution, the degradation of the image becomes noticeable, and while our eye can't detect all of the brightness levels in the higher radiometric resolution images, for computer processing, the increased sensitivity can become important in identifying and separating features. Another look comparing a full 24-bit color image with an image containing only 4 bits or 16 colors. One can see less spectral detail in the latter image. Next, I want to take a look at a few specific sensors to give you a sense about what is out there. There is a whole host of sensors on various aircraft and space-based platforms that are flying or orbiting overhead, collecting information about the Earth's surface that can be used to help us make informed decisions about what is happening on our planet. Many of these are similar in spatial and spectral resolution, while some are designed to look at specific phenomena such as atmospheric aerosols or sea surface temperature. For the purposes of this discussion, I want to focus on 4 land imaging sensors. These are MODIS on the Terra and Aqua satellites, the Thematic Mapper and Observational Land Imager on Landsat 7 and 8, the Worldview satellite, and aircraft-based high-resolution imagery. To further impress upon you the abundance of imaging systems, this graph provides examples of satellite-based sensors plotted over time along the horizontal axis versus the spatial resolution of the image along the vertical axis. As you can see, the spatial resolution of sensors has generally gotten smaller over time as technology has improved. The black squares represent panchromatic or grayscale sensors, and red circles represent multispectral sensors. You should notice the smaller spatial resolution sensors, those with less than 1 meter spatial resolution, are all panchromatic sensors. The MODIS sensor has coarser spatial resolution with high spectral and temporal resolution. Landsat has a moderate spatial resolution sensor with moderate spectral and temporal resolution. Worldview 2 has high spatial resolution and moderate spectral resolution and variable temporal resolution because it can be pointed to provide frequent coverage of a location. Aerial imagery tends to have high spatial resolution with moderate spectral resolution and low temporal resolution because it is not cost effective to fly often. MODIS, or the Moderate Resolution Imaging Spectroradiometer, is a sensor on board the Terra and Aqua satellites. It collects data in 36 discrete spectral bands at varying spatial resolutions. Band 1 and Band 2 are red and near-infrared bands at 250 meter spatial resolution. You should remember that this region of the electromagnetic spectrum is important for vegetation assessment. Bands 3 through 7 are blue, green, and shortwave infrared bands at 500 meter spatial resolutions. Bands 8 through 26 are various visible near and shortwave infrared bands at 1,000 meter spatial resolution. The remaining bands, 20 through 36, are thermal bands, also at 1,000 meter spatial resolution. Due to the large aerial extent of the MODIS sensor, we are able to get a global coverage every 1 to 2 days. This high-frequency temporal resolution is very important because it allows scientists to closely monitor dynamic phenomena occurring on the Earth's surface. And while the MODIS sensor does not have a high spatial resolution, it would not be suitable for localized analysis. It does give us a good view at the statewide or regional level, as with its natural or true color composite image and color infrared composite of southern New England. As you can see, when zoomed in, the spatial information is somewhat lost when compared to a Landsat image of the same area showing the UConn campus of Willimantic region. The value in MODIS is with a number of available spectral bands and frequent coverage of an area. Landsat is a series of satellites first launched in 1972, and the mission continued to provide global coverage of the Earth's surface today. Landsats 1 through 5 carried the multispectral scanner, which had 4 spectral bands at 80 meter spatial resolution. Landsats 4 and 5, in addition to the MSS, also carried the thematic mapper, which had 6 reflective bands at 30 meter spatial resolution, and a thermal band at 120 meter spatial resolution. Landsat 6, launched in 1993, carried the enhanced thematic mapper sensor, but failed to reach orbit and now rests at the bottom of the Indian Ocean. Landsat 7, launched in 1999, also carries the enhanced thematic mapper, which includes a 15 meter spatial panchromatic band and reduces the spatial resolution of the thermal band to 60 meters. The most recent satellite, Landsat 8, was launched in 2013. It carries the operational land imager, which collects 8 spectral bands at 30 meters, plus a 15 meter panchromatic band, and the thermal infrared sensor has 2 thermal bands at 100 meter spatial resolution. A single Landsat scene is 185 by 185 kilometers, slightly larger than Connecticut. In that 30 meter spatial resolution, it gives us a pretty good spatial representation of the Earth's surface. Landsat has a 16-day revisit period, meaning it flies over a location every 16 days. It is, however, the combination of spatial resolution and spectral resolution that makes the Landsat image an ideal choice for many scientific studies and monitoring projects. Looking specifically at Landsat 8, here are examples of 6 of the 8 reflective bands. The blue band, the green band, the red band, all provide a somewhat similar reflectance, meaning that they are correlated. The near-infrared band looks different due to the high reflectance of vegetation in the near-infrared portion of the electromagnetic spectrum, and the 2 middle infrared bands. Looking at 3 visible wavelength bands together, blue, green, and red, provides a natural color composite. So the greens here are vegetation, the dark features are water bodies, the white bright features are built up urban features and bare soil features. Viewing the near infrared green and red bands together provides a color infrared composite. Healthy green vegetation will appear red in this band combination due to the high reflectance of vegetation in the near infrared wavelengths. And viewing the near infrared and both middle infrared bands together provides a reflective infrared composite where vegetation is red, water bodies are black, and non-vegetative surfaces are shades of cyan and blue. Here's a comparison of near-infrared color composite Landsat imagery with higher spatial resolution aerial imagery. WorldView 2 is a commercial high-resolution satellite sensor launched in 2009. As the chart and graphic shows, it collects data in 8 separate spectral bands. These are at spatial resolutions of 1.85 meters. It also collects a panchromatic band at a spatial resolution of 46 centimeters. This sensor has the ability to be pointed at specific targets, so it can have a repeat temporal resolution of approximately 1 day. Here's an example of WorldView 2 imagery viewed as a natural color composite using the blue, green, and red bands. The spatial resolution is very good for flying at an altitude of 478 miles. Here's an example of a color infrared composite using the near-infrared red and green bands. Being a leaf-on image, there is a lot of red due to the abundance of vegetation. Water features stand out as black. This composite uses the near-infrared, red edge, and red bands. The importance of the red edge band is that it is detecting the rapid change in reflectance for vegetation from the red region of the electromagnetic spectrum to the near-infrared region, which allows us to better evaluate vegetation health and identify vegetation type. Lastly, here's a look at the 46 centimeter panchromatic band. Higher spatial resolution panchromatic bands can be fused with the multispectral bands to improve the spatial characteristics of the imagery while maintaining spectral characteristics in a process called pan sharpening. Aerial orthoimagery will typically provide the highest spatial resolution of available imagery. It is considered orthoimagery because any topographic distortions have been removed so locations are accurate on the image. Here is an example of a natural color leaf-off aerial image with 1 foot spatial resolution. And a corresponding color infrared image. The inclusion of the near-infrared band allows for a stark contrast between the water, dark areas, which has low reflectance in the near-infrared region, versus the vegetation, red areas, that is highly reflective in the near-infrared region. Here are a couple examples of 1 meter spatial resolution nape imagery captured during the summer. The first is the true color composite of blue, green, and red visible energy. And the second is a near-infrared color composite. One thing to note in this image is the difference in reflectance of the two large water bodies. The one in the center and bottom of the image appears darker, meaning it is absorbing more energy, while the water body at the top of the image appears slightly brighter in comparison. The brighter appearance is due to more sediment or other particulate matter being found in that particular water body when compared to the other. This is one way we can quickly assess water quality issues. Next, I would like to quickly share some sites that can provide you access to remotely sensed imagery for Connecticut. First, some aerial imagery resources. Recent image data can be found at the Connecticut Ecological Conditions Online or CTECO website. Not only can you view the imagery online, but you can link the imagery in your GIS. Additionally, current and historical imagery can be found at UConn's Map and Geographic Information Center, or MAGIC. This includes the historic 1934 aerial survey of which Connecticut was the first state to fly a statewide aerial mission. The Natural Resources Conservation Service and the USGS both provide access to various aerial imagery, such as 1 meter spatial resolution nape imagery. Here is an example of historic black and white aerial imagery from a 1980 flight that can be acquired through the USGS Earth Explorer website. The original scale of the photograph is 1 to 80,000, and it has been scanned into a digital format where 1 inch equals roughly 6,700 feet. This is an excellent source of some historical imagery. Access to public domain satellite imagery in the form of Landsat and MODIS can be obtained through the USGS at either the Global Visualization Viewer or GLOVIS or through their Earth Explorer website. MODIS data can be found through, here's the GLOVIS user interface. By clicking on the Collections tab, you can view available image data from various image sources like the Landsat archive. MODIS data can also be found through GLOVIS and Earth Explorer, but also through the MODIS Reprojection Tool web interface. These sites are free, but require you to register. Here is the MODIS Reprojection Tool web interface. By clicking on the Product tab, you can view available MODIS image data layers and select those you would like to download from the archive. There are a number of commercial sources of satellite imagery also, but these will cost you. The WorldView 2 imagery can be viewed at the Digital Globe website, and Spot Imagery, a French satellite, can be found at the Spot Image website for a couple of examples of commercial imagery. Lastly, I want to take a look at the results of some image analysis processes that can be performed through software such as Esri's ArcGIS. Many of these analysis tools can be found in other GIS and image processing software. The specific analysis are the calculation of the normalized difference vegetation index, measuring thermal emissions, and high-resolution land cover classification. One of the more common uses of remotely sensed imagery is for the calculation of the normalized difference vegetation index, or NDVI. NDVI is a numerical indicator that uses the near-infrared and visible bands from an image to assess whether an area being observed contains live green vegetation or not. This is one of the reasons so many sensors collect just visible and near-infrared energy. The NDVI output is a ratio, so values are ranged from -1 to +1. The more vegetation and the healthier the vegetation, the closer to +1 the value will be. Here's an animation of NDVI layers for the Greater Connecticut area for 2014. The NDVI layers were derived from 8-day composites of MODIS satellite imagery. The images are all scaled the same. You will notice the greening up of the area as the growing season gets underway. By July and August, we are at full leaf-out growing conditions. As we move through September and into the fall season, vegetation senescence has set in. Leaves are dying and the vegetation is going dormant, resulting in the decrease of the greenness into December. Here are 3 images of MODIS, Landsat, and NAPE aerial imagery and the resulting calculations of NDVI for each. As you can see, the spatial resolution of the imagery has a significant impact on the resulting NDVI output. As you can see, the spatial resolution of the imagery has a significant impact on the resulting NDVI output. For the MODIS imagery at 250 meters for this region, every image pixel will contain a certain amount of vegetation, so we would expect positive values of NDVI for all of the pixels. For Landsat at 30 meters, we would still expect most pixels to contain some amount of vegetation, and again, most NDVI values would be positive. Using NAPE imagery at 1 meter, there will be a mix of vegetated and non-vegetated pixels, so NDVI values will range across negative and positive. And I see we have a question about the NDVI.
Amma asked the question, is NDVI always reliable? It is a standardized metric. It's widely used in a number of programs operationally for monitoring global biomass, local biomass as well. There are ways to calibrate the NDVI into actual measures of biomass. It's again, MODIS was designed, the first 2 bands were designed specifically for NDVI. There's also one called EVI, which is the Enhanced Vegetation Index, which is simply a variant of NDVI. So to answer the question, if you have a sensor that has a red band, a chlorophyll absorbing band, a near-infrared band, in which reflectance is relatively high for vegetation, then you have a standardized metric of the extent and perhaps the vigor of live, healthy green vegetation.
Thanks, Dan. Moving on. Energy is not only reflected off of Earth features, but these features can also emit energy, typically in the form of heat or thermal energy. The features absorb the energy and release it over time, and certain sensors are designed to collect energy in that part of the electromagnetic spectrum. As an example, I want to take a look at the outflow of water from the Millstone nuclear power plant. There was an article in the June 22nd edition of the Hartford Courant titled, "Are Millstone's Nuclear Plants Adding to the Sound's Warming Problems?" Millstone, located in Waterford, Connecticut, in the southeast part of the Connecticut, draws about 2 billion gallons of seawater a day to cool their reactors and then pump the heated water back into Long Island Sound. Although the plant's operators and Connecticut state environmental officials say there is no scientific evidence that the hot water from Millstone is having any significant impact on overall temperatures in the Sound, many people claim, obviously, Millstone creates thermal pollution. But the question is, to what extent? Landsat imagery provides us a way in which to spatially visualize the extent of the thermal plume flowing from the power plant. The nuclear facilities permits require that the plant's discharged waters must not have any significant heating impact beyond 8,000 feet, or approximately 1.5 miles from Millstone's outlets into the Sound. The plant would violate the permit if temperatures beyond that limit were increased by +4 degrees above the overall average water temperature in the Sound. Thermal energy collected on January 4th, 2014 from the Landsat 8 satellite shows the plume of warmer water flowing from the Millstone power plant. The calibrated thermal imagery shows the Long Island Sound average water temperature as being about 35 degrees Fahrenheit. The average temperature of the plume is calculated at about 40 degrees Fahrenheit. The plume is only about 3,600 feet long, so there is no significant impact of the plume beyond its permitted area. Looking at the plume on a late summer day in September 17, 2014, the average Long Island Sound temperature is about 67 degrees Fahrenheit. The plume is about 74 degrees Fahrenheit. While about 7 degrees higher in temperature, the plume extends about 1,900 feet, so again, within the permitted parameters. So on these two dates, at that particular time, it is safe to assume there is no significant impact on Long Island Sound water temperatures beyond what is permitted. A last example looks at the use of multiple sources of high-resolution imagery to derive land use information. Input sources of information include 1 meter spatial resolution NAPE imagery, 1 foot spatial resolution digital aerial imagery, 1 meter spatial resolution LiDAR imagery depicting the bare earth elevation, and 1 meter spatial resolution LiDAR imagery depicting surface elevation, which includes building heights and canopy heights. Using the spectral and spatial information from the imagery and adding the elevation data processed together, we are able to take the specific information provided by each data type and depict a spatially detailed land cover map. With that, it brings us to the end of this webinar. We would like to leave you with this parting thought by the English astronomer Sir Fred Hoyle, relating it to what remote sensing permits us to do. He stated, "Once a photograph of the Earth, taken from outside, is available, once the sheer isolation of the Earth becomes plain to every man, whatever his nationality or creed, a new idea as powerful as any history will be let loose." Remote sensing permits us to see the Earth in a very different way, over a broad expanse, so we can see how Earth features are connected, and this enables us to create new ways in which to examine our planet. Well, I hope we have been successful in providing you with a basic understanding of remote sensing and the technology. Of course, it is more complicated than what we have presented here, but we hope you can now look at a remotely sensed digital image and know more about what it is showing you. It really is more than just a picture. And now, we would be happy to take a few questions.
And if you'd like to ask follow-up questions after this webinar concludes, James and I have provided our contact info, and we'd be happy to entertain and try to answer your questions. Also, we're planning a webinar for a follow-up webinar, likely in October, that will talk more specifically about Landsat, its applications, and how to do some of those things within something like ArcGIS Desktop. So look forward to something hopefully in October. Question from Vivian. How widely used is remote sensing across the state of Connecticut? Remote sensing data are ubiquitous. Everybody probably to some extent is a remote sensing analyst. If you use Google Earth, Google Images, Google Bing Imagery, you'll be, you count yourself into the remote sensing analyst category. In terms of operationally, I would say in the state level, the local level, NGO, educational capacity, it's hard to put a number on how widely it is used, except to say that it is widely used. Huge investments are being made by the federal government, state government, and even municipalities in the acquisition of data for operational program use. Question from Donald Murphy. What remote sensing system might be useful to map eelgrass distributions in shallow coastal waters? There's actually a program within the NOAA Coastal Services Center that maps SAV, submerged aquatic vegetation, using mostly water penetrating capabilities afforded by a blue-green film, or a sensor that emphasizes sensitivity in those portions of the spectrum where the transmissivity is greatest in the water column, and also using water penetrating LiDAR. A LiDAR that operates in the blue-green portion of the spectrum, again with the transmissivity of the water columns greatest, such that one can detect the submerged aquatic vegetation. Also, for our upcoming webinar in October, since we are still yet articulating what will be in it, if you have some areas of interest that you would like James and I to consider incorporating to that webinar in terms of applications of remote sensing, we'd be happy to address those as well. If you go, there's a question from Vivian again, any evidence of global warming using this tool? Yes. If you go to the NASA website, the Scientific Visualization Studio, if you just Google search that, you'll find it. You'll find a number of animations that show, through the use of MODIS and other satellite data, the global warming through time. They're really great visuals for educational purposes, but also demonstrating clearly the changes in global sea temperature as well as land surface temperature. So I would recommend go to NASA SVS.
There's another question from Kevin. What are the data constraints in terms of storage and then processing in a GIS for application with regard to increasing spatial resolution? Are there potential big data needs for integration for large areas of studies, such as the entire USA?
Big data is a good argument to make with respect to remote sensing. As you increase the resolution by, let's say, a factor of 2, you increase the size of the data set by a factor of 4. A single Landsat image covering a good part of the state of Connecticut would take thousands, literally thousands of aerial photographs at finer resolution to cover the same area. So more images taken at different dates probably, as well as a huge volume of data storage. LiDAR, for an example, is a good data consumer. The LiDAR data for eastern Connecticut, which were acquired in October, November 2010, are about 2 gigabytes, so huge data sets. Is there an effort to put together global and or continental US data sets? They exist. There are seamless data servers, the national map, the geospatial data gateway, whereby you can search for, identify, and download some high resolution data.
Okay, looks like that's the end of the questions. I wanted to thank James and Dan for an excellent presentation and overview of remotely sensed imagery. I found it very educational and interesting. So once again, this was recorded, and we will post it on our website, clear.uconn.edu, in the next couple of days. And so for your friends who were not as smart as you and did not sign up for the webinar, you can send them the video recording. So thanks again for tuning in, and be looking for our fall webinar series, which will be announced the next week or two. Thanks very much, folks.
Thanks, James, and thanks, Dave.